Guys. So in this question, you have a fuse wire of radius zero point 0.2 millimeters, and this fuse wire blows out for a current of 5 amperes. That is, when a current of 5 ampere passes through it, this will blow off or it will melt in a way, right? So for what current, another fuse wire of the same material, but of radius zero point 0.3 millimeters will blow out in this case, right? So let me take this question, as an example to explain how to solve these kind of questions where you need to understand the working of a fuse wire. Okay, so we know when current passes through a resistor. So let me take a cylindrical wire only, and let's say you have a current I passing through it. So we know that when there's a current I passing through a cylindrical wire, this will give out heat, and the amount of heat which is being produced over here, the amount of heat produced due to current, that is heat dissipated by resistor, is equal to nothing but it's given by the formula I squared R. Heat dissipated by resistor will be equal to I squared R. Right. So this is the amount of heat which you can say is going to the wire, right? Or amount of heat given out to the wire per second, right? And now because of this heat, the temperature of the wire increases, right? But we'll now be considering that this wire is at a surrounding which is at a temperature of T naught, right? So this wire will be gaining heat from because of current passing through it, but this wire will also be giving out heat right now, right? And the amount of heat which this wire gives out, the amount of heat given out by this wire, that is based on Newton's law of cooling, right? We'll say that this is a object of temperature T. So we'll say that we are writing the equilibrium condition basically when this has attained a constant temperature T. So we'll say that this is a wire which has attained a temperature T in a surrounding of temperature T naught. So the amount of heat which it gives out will be proportional to T minus T naught. And it's also proportional to the surface area of this wire. It's also proportional to the surface area of the wire. So the amount of heat, this is your idea of Newton's law of cooling, which we'll have to make use of over here. So when we consider this in equilibrium, that is when this wire has attained some temperature T, then we'll say that the amount of heat going into the wire should be equal to the amount of heat going out of the wire. So I'll take both these proportionality constants and say that the heat given out by the wire is equal to some K into surface area. So I'll write surface area in this case as 2 pi RL into T minus T naught, right? Okay, so then you can see that, so basically this wire is blowing out because now this temperature T which this wire has attained is kind of equal to the melting point of the wire, right? So when it reaches this temperature T, you can say that this wire blows out. So from this we can get a relation between, what is the current value required to blow out a wire. Okay, so if I take R over to the other side, so I'll say that I squared is equal to K into 2 pi RL into T minus T naught divided by resistance of the wire. And resistance of the wire is nothing but rho L by, so that we equal to rho L into pi R squared, right? Okay, so if you want to know, so this is, in other words, what we have derived over here is that we have derived a relation between what should be the current flow in a wire to blow out the wire or to make that wire melt, to make that fuse wire melt right now. And if you want its relation with radius, then all the other terms are constant over here. This wire blows out at temperature T. Temperature T naught is a constant over here. Rho L is a constant. So the only thing which we need to consider its variation with right now is radius. So from this you can see that I squared is proportional to R cube, right? So this is the relation which you'll have to make use of in this question, right? So then if I now make use of this idea in this question, then I'll say I in the first case divided by I in the second case should be equal to radius in the first case divided by radius in the second case whole cube, right? So what was my current in the first case? Current in the first case was 5. Current in the second case is what we need to calculate over here. So that will be equal to 0.2 millimeters divided by 0.3 millimeters whole cube. So we'll get I2 value to be equal to 5 under root of 3 by 2 whole cube. Right, so this value will be equal to 5 into under root of 27 by 8. And this option is not there in the question, right? So, but this is the right answer for this question. This should be your answer for this question right now, right? So what I wanted to realize is this important relation. I think I've come across this question twice before. So this is your idea for this question, which you'll have to use. And this is your logic behind why we need to use these equations, or the logic behind why we need to use this idea to solve these kind of questions, right? So hopefully this question makes sense. See you guys in the next question.